So let's try this. We'll rewrite the integral 0 to 3, integral 0 to 4, integral y over 2 to y over 2 with a plus 1 there, of 2x minus y over 2 plus z over 3 dx dy dz. We're going to rewrite this with the transformation u is equal to 2x minus y over 2, v is equal to y over 2, and w is equal to z over 3. So, using some basic algebra, I promise that the algebra is not going to be too much work, but you should give it a try. We're going to skip it here just because we're going to otherwise just do too much little algebra. The inverse transformation is going to be x is equal to u plus v, y is equal to 2v. That's not too surprising that y could just be 2v, and similarly not too surprising that z is just going to be 3w. Not a lot of work goes in there. The hardest work is getting x equals u plus v, and even that won't be too much work. So give it a try. Now, let's write out the Jacobian. So partial derivative of x, y, and z with respect to u, v, and w. So we have a 3 by 3 determinant. And first row, partial derivative with respect to u, v, and w. So 1, 1, and 0. Then partial derivative of y with respect to u, v, and w. So 0, 2, 0. Partial derivative of z with respect to u, v, and w would be 0, 0, and 3. And we won't work through all of the determinant calculation, but you'll get the number 6. Now, the boundary pieces of the region E that we're integrating over, just staring up at this right here, the boundary pieces are, well, there's x equals y over 2. There's x equals y over 2 plus a 1. There's, based on the middle integral, y equals 0. There's y equals 4. Based on the outermost integral, there's z equals 0, and there's z is equal to 3. Then, let's see what each of these become, right? So these 6 equations each, what happens to each of them, these become, just by making the replacements. So x is u plus v, right, from right there, equals y over 2. So y is right there, 2v. Okay, so 2v over 2. And when you simplify this, let's write down what it simplifies to here. So 2's cancel, so you have u plus v equals v, subtract v on both sides. You're really, in the end, just going to get u is equal to 0. I don't want to show too much work here. The next one, after replacements, u plus v to replace the x, 2v to replace the y, still over 2, then plus a 1. This equation is going to become u is equal to 1. What about 2y is equal to 0? Replace the what about y is equal to 0? Replace the y with 2v. So just a direct literal replacement first is 2v is equal to 0, but then you divide by 2 on both sides, you get v is equal to 0. How about y is equal to 4? That becomes 2v is equal to 4. You end up with v is equal to 2. And then z equals 0 becomes 3w is equal to 0. Divide both sides by 3, and you get w is equal to 0. And then z is equal to 3 becomes 3w is equal to 3, and so you end up with w is equal to 1. What's really neat is that we actually just have constants as the bounds for u, v, and w. We just got really lucky that in the new three-dimensional space, in the xyz, in xyz we had something else going on, but in u, v, w, in that new geometric space, the integration space is just a box. And so we'll have integral, the function f from right here. Let's copy paste this down here. There's just all of these pieces that are needed. So let's do this. Okay, putting this, let's say, right there so that we can hopefully stare at more of what's going on. Okay, so we'll have integral, integral, integral. Then let's write down what's in the parentheses here. So 2x is up here. It's u plus v minus, and then y, which was 2v. This is all over 2. Then plus z over 3. Well, z was 3w. Of course, a lot of this cleans up more, but I'm not interested in messing with all that right now. The dx, dy, dz becomes the 6 there, the Jacobian, times du, dv, dw. And then since u is on the inside, we see here it goes from 0 to 1. V goes from 0 to 2, and w goes from 0 to 1. Again, just a reminder that this 6 here, this is due to the Jacobian. All right, so as the interactive question, let's have you do the following. This will be really good. I mean, this will be good in terms of doing some algebra, some trigonometry, some really digging into the Jacobian. But instead of, so let's describe the following transformation. So it'll be x equals y equals z equals things, but instead of writing a formula that has u's, v's, and w's, I would just like to write rhos, phis, and thetas. So how about if x is rho times sine of phi times cosine of theta, and y is equal to rho times sine of phi times sine of theta, and z is equal to rho times cosine of phi, then you should compute here the Jacobian. So partial derivative of x, y, z with respect to rho, theta, phi, and compute, show the work that this is going to become. Look, I'll just give away the answer, right? That the answer here is going to end up becoming rho squared times sine of phi. But you should show the work, right? So there's definitely lots of steps in here that you should show. The whole point of doing this, though, right, is to note that this is why dx, dy, dz, when converting to spherical, to an integral written in spherical coordinates, is going to become rho squared sine of phi, d rho d theta d phi, or whatever order you really want here. But the point is this rho squared times sine of phi is from right there. It ends up being the Jacobian. So the point of this exercise is to just go through the steps, take that information right there, compute the appropriate 9 separate partial derivatives that you need to, each of the variables x, y, z, partially differentiated with respect to each of the variables rho, theta, and phi, organize this in a 3x3 matrix, take a determinant, do a little bit of trig identity stuff. It shouldn't be too bad. It's a little tedious, but it's not challenging. It's just tedious. Go through it. Make sure that you get rho squared times sine of phi.